All right. Today, by the end of the lesson, you'll be able to describe how a charged particle is forced magnetically as it travels through a magnetic field. Use your right hand to determine the direction of magnetic force, magnetic field, and velocity. Calculate and determine the direction of magnetic force acting on a moving charged particle. And on Monday, we'll figure out how to calculate and determine the direction of magnetic force acting on a wire with current flowing through it. Foundational fact number 2. If a charged particle is moving perpendicular through an already existing magnetic field, then it will experience a magnetic force that is perpendicular to both the velocity and the field. That's a mouthful for a foundational fact. I have no idea what it means. All right, so for each foundational fact, there is a right-hand rule. Okay? So right-hand rule number 2. We'll look at that here momentarily. So, here's our stage. You have a horseshoe magnet, North Pole, South Pole. Keep it easy on your notes. You draw this two-dimensionally. Okay. Which way is the magnetic field going between the uprights of the horseshoe magnet? Out of north into south. Remember from your magnet lab how they went straight across. Okay. So that is your magnetic field. What we're going to do is we're going to shoot a positively charged particle between the uprights. We're shooting a field goal. Okay. So here we're shooting it this way. The velocity is positively charged. So if we're looking at this two-dimensionally, so we got the magnetic field going this way, and the velocity going this way. See how these are at a right angle? Okay, so how would I draw? So here is looking this way. Does that make sense? Just drawing it two-dimensionally. What should I put here? Circle with a dot or circle with an X for velocity? Is the velocity coming at you or going away from you? Coming out of the board at you. What do we draw? Circle with a dot or circle with an X? You're about to be shot by the arrow, you're like, oh, duck. You're looking at the arrowhead, the tip. Good with that? That is your velocity. All right. Right hand rule number 2. Get your right hand out. Okay. Show me right hand rule number 1. Okay. Your fingers correspond with what? Magnetic field. Okay? Your fingers in right hand rule number 2 still correspond to magnetic field. The only exception is you're not curling it, you're keeping it flat. Not curling it, but keeping it flat. Okay? Your thumb in right hand rule number 1 corresponds with what? Current. Okay? It will continue to be current in a wire, but it also can represent velocity if you're talking about a charged particle. But both signify which way things are moving. Good at that? Okay? The way I remember this is like your thumb is kind of like hitchhiking. I know we don't do these hitchhike nowadays, but you've seen movies. Okay? It shows you which way you're going. Your fingers, they're mini field. There's many fingers. A lot of field vectors, a lot of field lines. Okay? A lot of fingers. So, what you're going to do is you're going to stick, and then we'll get to your force here in a second. We're going to stick our fingers which way? Which way we're sticking our fingers? Sticking our fingers to the right, because that's the same direction as magnetic field. Everybody okay with that? And we're gonna lock that in there. We're gonna in IED terminology, we're gonna constrain it. We're going to commit our fingers to the right. Okay, so now we can pivot this, but we cannot, don't do this. You locked in, you're committed to that. Don't let go of that. Okay, so now you're just gonna pivot this. What part of your hand corresponds with velocity? Your thumb. So you're gonna rotate it until your thumb is going out of the page. Now, the force corresponds with your palm. Which way your palm pushes. Which way is your palm pushing? Up. This is the direction of your magnetic force on a charged particle as it goes through this magnetic field. Okay. So, here, the charged particle is moving perpendicular to already existing magnetic field. So we had this thing is going this way, it's perpendicular. All right, everybody see that? Perpendicular to already existing magnetic field. Then it'll experience a magnetic force that is perpendicular to both the velocity and the magnetic field. Here we have the x-axis, we have the y-axis, and we have the z-axis. All three of those are perpendicular to each other. All right with that? Okay. A popular follow-up question is why? I mean, that's just, and my response is, it does. It's foundational fact. Number 2, just does. Okay. So, and we're going to use our right hand to figure out which way it's going to be forcing. Okay? The exception to this is if you have a negative charge. So if you have a negative charge, then magnetic force is the way is acting in the opposite direction. Which is in the direction of the opposite, sorry, it's in the opposite direction, which we're going to use the back of the hand. Okay. So if you have a negative charge, we're going to hold our hand exactly the same way. Fingers are still going to the right. Thumb is still coming out of the page. But instead of pushing with your palm, you push with the back of the hand. So magnetic force would be doing that. That. The way that I remember that, palm pushes positive, okay? And if you get backhanded, that has a negative connotation. Best I got. Okay? So, the rest of the day is going to be devoted to getting you familiar with the right hand rule. Okay? Any questions so far? All right. So, what part of your hand corresponds with B? Fingers, your magnetic field. So stick your fingers going which way? Up. Okay. What part of your hand corresponds with velocity? Thumb. So we're gonna lock our fingers up. We're gonna rotate with our fingers up until our thumb is facing which way? Circle a dot coming at us. So the force is represented by what part of your hand? Palm, because it's positively charged. Palm pushes positive to the left. Okay with that? Give you a little time to work on that one. So this test is always fun because everybody's like, I have to discern if you're like asking the question, just using your right hand rule. But like, yeah, it's a thing. Okay. Fingers go which way? Circle an X into the board. So now we're locking that in. Okay. Actually, let me do it a different way, just to like mix things up a little bit. Let's look at velocity first. So what part of your hand corresponds with velocity? Thumb. So we're going to stick our thumb to the right. We're going to lock this in here. Okay. So B corresponds with fingers. So you keep your thumb to the right and you stick your fingers into the board. It is negatively charged. So which way is it going to be forced? Back of the hand, downward. Good? Okay. Heads up. I gave you the force, not the field. You're looking for the field. Share with your neighbor, see if your hands match.
We don't know. It'd be the palm. Palm faces the left, right? So that's the force. Your palm. If your palm is facing left, so the thumb is facing into the board. That means your fingers are going down. And if your thumb is velocity, which is going into the board.
I don't know how I got to this point. I must be falling asleep.
Okay. What part of your hand? Thumb goes which way? into the board. So we're locking this in here. Okay? What part of your hand corresponds with force on a positive charged particle? Your palm. So you're going to rotate until your palm is facing left. Okay? You're looking for your magnetic field, which corresponds with what part of your hand? Fingers. Fingers are going down. Correct answer is down. How'd we do? Get it?
It was hard to do that,
Try that one. Okay. Great question. That rest. No force. Okay. A charged particle is not going to interact with a magnet unless it's moving. Get at that? No force at all. Has to be moved. Give that one a shot.
So the circles.
Dude, it's so hard to do because the force is down because
Oh, it's negative.
and then it's hard to force on board.
But it's oh wait.
Oh, yes. I have what you mean.
Show your neighbor.
It's a negative, which means it's the bacteria.
But if it's the best one,
Good. Doesn't matter which one you pick first, but you need to pick something. I'm going to pick magnetic field. Fingers are going out of the page at you. So you're like doing this. Okay? What part of your hand corresponds to a force on a negatively charged particle? Back of the hand. So I'm rotating it until my back of the hand is down. So what part of my hand corresponds with velocity? Thumb, which is facing to the left. Yes? Doing okay? If a charged particle is moving, what? Is there any component of that velocity that is moving perpendicular to the direction of the magnetic field? No, it is moving parallel. So the answer is no force. G. You okay with that? No force. There has to be some component that is perpendicular to the direction of the magnetic field. Okay? So that leads us to a word problem. Particle with a charge of negative 33 microcoulombs moving at 2,000 meters a second through at 40 degrees through a 6.5 Tesla magnetic field. What is magnitude of magnetic force on the charged particle? Okay. So our equation is equal to magnetic field times the charge times the perpendicular component of velocity. This is component of velocity that is perpendicular to the magnetic field. Okay? So, is there a component of velocity? So this is not three-dimensional. This is like this arrow is in the plane of this board. So is there a component of velocity that is perpendicular to the magnetic field? That would be the component that is perpendicular. I could draw it over here, or I could draw it over here. Either one is fine. So, to find that component that is perpendicular, am I going to use sine or cosine? I'm going to use sine of 40. Okay with that? It's been a while since we've done trig, this class. Okay, so I'm going to go sine of 40 is equal to velocity perpendicular over 2,000. Or I could write it as 2,000 times sine of 40 equals velocity perpendicular. Based on what I did last class, it's 1286. 1,286 meters a second. So, my magnetic force is equal to 6.5 Tesla. So Tesla is the unit for magnetic field. Elon Musk got it from Nikola Tesla. This was the unit for magnetic field way before electric cars. 33 microcoulombs, sometimes 10 to the negative 6th. Again, we're going to drop the positive and negative sign on the charge in the math, multiplied by 1286 meters a second. And when I do that, I find that to be 0.28. And what's the unit? It is a force we're going to use newtons. Good there? That's the hardest math you're going to do in this unit. Compared to first semester stuff, that's easy peasy. Yeah. Follow-up question is, which way is it being forced? Okay, so you're going to stick your thumb not in the direction of this, but in the direction of the perpendicular component. So, fingers are going to the right, thumb goes down. It's negatively charged. It's going to be forced into the board. Good with that? Questions there? Okay. All right. Demonstration for you. All right. This is called a cathode ray tube. This works by this is a transformer. We'll learn about that at the beginning of, or at the end of this unit. But what it does is it increases the voltage to like thousands of volts. So there's a voltage across here that is able to cause electrons to be ripped off of some of these atoms and on this negative plate and being shot this way. Okay? And so the reason you're seeing them is because the gas inside. In chemistry, did you guys do like flame tests or like neon tubes and you like saw stuff? Do that in regular as well? I'll have to do that. So different gases have different colors associated with them depending on how when their electrons get excited, they jump up to a certain orbital and they fall back down and emit light, certain frequency. This happens to be green. Think it's nitrogen, I'm not positive. But, so it's exciting electrons in the gas and you can see it. So here's what you need to know. Electrons are being shot this way. Okay? I have a pretty strong horseshoe magnet here. The north pole is the south pole. So this is north, this is south. Which way are the magnetic field lines going in between here? North, south, going out of north into south, outside the magnet. Good with that? Okay, so field lines are going this way. I'm going to hold it that way. So you got north pole, south pole, yep. So field lines are going at you. Okay, I'm going to hold it like this. Which way are the electrons going to be forced? So electrons are going this way. Magnetic field is going that way. Which way are electrons going to be forced? Show me with your hand. You just got to embrace it. Like, your fingers are going which way? So stick your fingers that way on your right hand. Your thumb's going which way? And they're electrons, so they're going to be forced you get it? And forced up, yes? Okay. If I flip this around, which way is it going to be forced? Your fingers are going towards me. Yes? Okay. Pull that. Okay. These old school TVs are known as CRT TVs. CRT, cathode ray tube. Okay? They have one of those. They have one of those cathode ray tubes in here. Look at the diagram on the board. Okay? You have an electron gun shooting at the screen. Okay? Old movies, when they see a TV, you get those bands that are like in the films and stuff. Okay? The way these work is they shoot electrons across like super fast, like a flip book, but going. So the frame rate of the film is off from the frequency that this electron gun's shooting, and so you get these bright lines going down. You don't see a picture, just bright lines. Okay, so. You guys hear that? That's like childhood right there. That was the good stuff. So this is like state of the art in college, in my college. Like this is like, no, it's like part of the TV. Like yeah, like dude, where'd you get that? That is the coolest thing ever. Okay, so. One of the rules was you couldn't bring a magnet near one of these TVs because the magnet is what's steering the electron beams to go where they need to go. So when you brought a magnet near, it like whacked it out. Okay? One time, growing up, I can't remember which kid it was, but we left some magnetic thing on the corner of the TV, and we like came up and like, Dad's gonna kill us. Like, so some of the higher end TVs had a degauss button that would like reorient the magnetic field, but if you didn't have one of those, which we didn't, you're left with like trying to like mess with it, like okay, we can think. Maybe. Think you can notice? I think we're good, right? Yeah, okay. Just turn off and walk away, okay? Good with that? So, cathode ray tube. Those in your existence, like grandparents, anybody have like a really huge, grandparents have a huge TV like that?
And we also had that in school.
Oh, do you? Nice. Good stuff. All right. So, tell me which way this is going to show me. Tell me which way that's going to get forced. There we go with up. So as time goes on, this thing's going to move to there, yes? This gets forced up. Now it's moving this way. Show me which way it's going to get forced. So as time goes on, it's now going to be moving up. Which way is it going to get forced? If this magnetic field is big enough, what would happen as time goes on? How is it going to move if this is all, it would continue to move in a circle? Why? Because the magnetic field is always acting perpendicular to the direction of motion. Okay? If I was a nice guy, I would make you do some problems like, hey, what's playing the role of centripetal force? And you'd be like, oh, FC is equal to FB. And you could do a whole bunch of math, just like with orbits. But I'm not a nice guy, and I'm going to make you suffer through that in college when you get there. But that's a thing. Okay? Good with that? So, if we shoot a charged particle through a magnetic field, it's going to go in a circle. This one's going in a spiral because it had some velocity going parallel to the direction of the magnetic field, which there's no force for that. So it's just spirals up. Good? Okay. So one application of that is particle accelerators. We get like a proton going really close to the speed of light with magnets going up in this warm-up loop, and then they send it off here. So this is in Europe, CERN. This one's Fermilab is in Chicago. So the idea is you get a proton going close to the speed of light, and then you raise a sacrificial target of some element in its way, and then you have that speed of light, or close to speed of light proton, just smack this, and you get the wreckage, but you want the wreckage to happen in a magnetic field. And you can see how just the carnage of the wreckage. But what they're looking for here, you get charged particles they're looking for undiscovered new subatomic particles. Some of them are positively charged and they spiral this way, some of them are negatively charged and they spiral that way. So they're just kind of looking at stuff, how you do it, okay? Another application are the northern lights.
The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. Then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm.
Okay, a couple things. Number one, plasma, fourth state of matter, solid, liquid, gas. As you go up, you become more and more energetic. Yes, solid, liquid, gas. Plasma is the fourth state where it's so much energy, electrons can't be held to the nucleus. Okay? So they're charged particles, they're moving. Moving charged particles create a magnetic field. Okay, that's what the rubber band was. Okay, that's not really rubber bands. Okay?
An invisible shield.
So,
The Earth's magnetic field deflects the storm.
two different magnetic fields.
Magnetic fields couple together and create a bump where the gas streams down on the daylight side.
If we
of the
didn't
pole.
if we didn't have
This
this,
is daylight aurora.
this would rip off our
Magnetic fields
atmosphere.
Stretch further back and couple together. The magnetic rubber band breaks. Gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Okay. So, Northern Lights. Did you guys see them a couple months ago when that happened? Like, that's so cool. Like, seeing them this far south doesn't happen very often, but the sun is kind of facing us in a way where it has these solar storms that are hitting us. So these charged particles from the plasma are going into our magnetic field, and you know the quarter funnel thing where you're like send the quarter around is like zzz, and like towards the end, so it's right here's going zzz, and it's hitting gas in our atmosphere, causing the electrons to be excited. They jump up, and then they fall back down and emit light, and that is the northern lights. Okay, this is a little bit fast forward. You can see cars traveling, but it's not crazy fast forward. So the different colors correspond to different gases. Nitrogen emits green, oxygen emits the red or the pink color. At least I saw a lot of pink back a couple months ago. Okay. Here is. I don't think about that. This is real time. Have a good weekend. If you need Christmas lights, let me know.
Are we allowed, like, for that thing to, like, for kind of like do use like things called? Can we like put like Harper up here and up here so there's like
Oh yeah.
okay.
Yeah, you've got lots of freedom.
I had it. I said that like 21.
You did. Yes, someone. Thank you. Someone brought that up. I will fix that.
Okay,
Good catch.
thanks. Online review.
Yes.
Okay, I wanted to talk to you about
Yes.
that one too. It's done, like I did 21.
Yeah.
Okay.
I got it fixed.
No, you're good.
Yeah.
And then from the day I was gone, I
Yes.
swore I could have shown you
You
this.
might.
Which is fine.
Yes. Shocked you now. Get fixed.
I could have sworn because I
You might. You totally could. Just. It's definitely.
There's my-
Thank you.